BC Chemistry, Unit 4. In this short video, we'll talk about how do we combine it together. So how do we actually, in terms of calculation, how does it look like when we're actually using a calorimeter to determine the heat of combustion? Now, here is an overall question. First of all, the energy content of food can be determined by completely burning a sample of food in bomb calorimeter and then calculating the energy released. Of course, we know that. Then the calorimeter is calibrated electrically. So the data given is here below: current, voltage, time, and temperature rise. Then the carbohydrate glucose is burns in excess oxygen in the following reaction. Well, not sure if the reaction is actually useful, but we're told that 1.324 grams of glucose was burned in the calorimeter, and then causing the temperature of the calorimeter to change from 18.23 to 35.55. Then calculate the molar heat of combustion, molar heat in kg per mole. Well, if you feel like, oh my god, I just read a very complicated story, what's actually going on? Now let's see what's actually going on. The actually useful information for us are actually, first of all, we're told that the calorimeter needs to be calibrated. That's step one, right? Then we use the calibrated calorimeter. So we have the calibration factor of that calorimeter. Then we put some glucose in there and we burn it. And then we recorded the temperature change. Now we are asked to determine the heat of combustion for that glucose. Okay? So basically, the question can be cut into two. The step one is calibration. So we need to determine the CF for that particular calorimeter. Once we determine CF, we can use that CF to determine actually how much heat was released by burning 1.324 grams of glucose, right? Then we can determine the heat of combustion in kg per mole. Now, let's see, part one. Calculating the calibration factor. We know that it's calibrated electrically, so E equals VIT equals that. Remember, the unit is joules, okay? So we literally just put the first three numbers together and multiply together. The product of it is the amount of heat we actually supplied for calibration. Then CF equals to E over delta T, and notice that this is the temperature change, temperature rise, as a result of we supplying heat manually in order to calibrate it, okay? Because later on we'll have another temperature change, which is a different consequence, okay? So our calibration factor therefore is determined as 1.18 kJ per degree. So basically, for every degree of temperature recorded, it's 1.18 kJ of heat that's released. Okay, so then the second step, the second part of the question, is to use the calibration factor to actually determine how much heat is released during combustion of 1.324 grams of glucose. Now, that's actually, if you know understand the logic, it just becomes, well, since the temperature increase as a result of combustion reaction is this much, okay? So I used a small delta T just to distinguish from the previous delta T that we actually used. This 17.32 degree is a result of combusting the glucose. Okay, that's step two, temperature, right? Then we use the calibration factor to determine, okay, since this is a temperature recorded, how much heat was actually released? Well, our calibration factor can tell us it's 1.18 times this temperature, the calibration factor times this temperature, and as a result, okay, so if temperature increased by this much, 17 something degrees, then the actual heat released should be 20 something kJ, okay? So this 20 something kJ is released completely due to burning 1.324 grams sample of glucose, okay? So how much glucose is actually there in moles? Okay, so glucose mass over molar mass, find out, okay, 0.007 something moles of glucose. So 0.00736 mole of glucose combusted caused a temperature increase of 20.4376. Now, what's the molar heat of combustion? Well, you just put the amount of heat released over the amount of glucose that actually used, and as a result, you know that, okay, the heat of combustion for glucose determined in this particular experiment is 2778.53 kJ per mole.